So I want to look at a surface S that is a parametric surface, and let's assume that it's parametrized by some R of U and V, let's say. Um, so the question is, if I pick a point right here, this point corresponds to some R of U naught, V naught. You plug in a specific pair U naught, V naught, and you're going to get out a point on the surface. And so I might want to know what the normal vector is to the surface at that point. And it turns out, let's just think about this as some generic point, R of U and V. So it turns out that the normal vector to S at a point R of U and V is given by, well, it's N equals, we're going to write it R partial U cross R partial V. And you are absolutely allowed to ask, what is R partial U? What does that even mean? That's not quite the way that we've used the language. Well, it's kind of a natural extension of the way that we've used the partial notation. So R partial U is you just take the partial U of each component. So X partial U, Y partial U, Z partial U, and R partial V is going to be X partial V, Y partial V, and Z partial V. So let's learn this via example. That's always the best way to do this. So we're going to find the equation of the tangent line to the surface that's parametrized like this. So here, I'm not asking you to parameterize anything. I'm giving you the parameterization, and I want you to find the tangent line at this particular point, U of 1 and V of 1. So we can start two different places. Let's actually find the point in space, the point on the surface that corresponds to this when U is 1 and V is 1. So let's realize that R of 1, 1, you can see is going to be the vector 2, 1, 1. That's our point. This is a point on the surface. The tip of this vector is a point on our surface. Now I need to compute R partial U. And so I get, this looks like a V. Let me make those clear. We have to be careful for the notation. R partial U is going to be 1, 2U, and 0. I'm just taking the partial derivative with respect to U of each component. I get R partial V is again 1, 0, and 2V. Now I can compute the cross product, RU cross RV. And let's see, what am I going to get? Well, I'm going to get 4 UV. So I'm going to get a 4 UV comma negative 2V minus 0, so negative 2V. And then I'm going to get 0 minus 2U, so negative 2U. I'm interested now in using this normal vector at my point. So I want RU cross RV evaluated when U and V are both 1, and I get out the vector 4, negative 2, negative 2. I'm going to get rid of the 2, and I'm going to use 2, negative 1, negative 1. I can do that. And so the point is the tangent plane, you just, the formula, you've got a point on the plane, you've got a point, the normal vector. And so what do? You say 2, this 2 is the 2 from the normal vector, times x minus 2. This 2 is the 2 from the point, plus, let's not say plus, let's say minus y minus 1. And so again, this minus 1 is right here, this 1 is right there. And then I'm going to say minus z minus 1 equals 0, or if you like, you can write this as 2x minus y minus z equals to 2. So I thought you might want to see what this looks like. So let's hop on over to Mathematica and have a look. Here we go. So I've gone ahead and graphed the surface. It's kind of this interesting blue surface here. That's what you get when you graph our parametric function R of U and V. There's the tangent plane. There's the point. I went ahead and popped the normal vector on there as well, and just wanted you to get a sense of what this looks like. So what's fun is, again, this surface is a parametric surface. where we're just plugging in u and v, just two variables, getting a three-dimensional surface, and yet we can still find tangent planes, normal vectors, so on and so forth, using the techniques that we just described. So wanted you to see that, and let's go on to the next video.